Hello everyone, this is lecture 12 of ComSci 142, Maximum Flow. In this video, we will discuss the maximum flow problem and start by introducing flow networks, and then we will discuss the Ford-Fulkerson method which we'll use to solve for the maximum flow, and then finally we will also discuss the minimum cut problem, which is a related problem to maximum flow. So let's start with flow networks. So if you're given a graph like this, you'll notice that there is a vertex S which acts as the source vertex because all of its edges are going outwards. So notice that no edges are going inwards towards S, or no incoming edges for S. So this is known as the source vertex. On the other hand, T here is known as the sink vertex because it only has incoming edges and no outgoing edges. Okay, so this type of graph is what we'll use for our flow network. Okay, notice that this is a weighted graph on the edges, and you can think of the edge weights as the capacity of each edge. So we'll explain in a while what that means. So since there is a capacity for each edge, okay, what we will do is we will transfer or flow some supplies from S, which is the source, to T, which is the sink or the destination. Okay, and our goal is to transfer as much as possible from S to T, passing by these edges, and we'll have to follow their capacity. So if this edge SC here only has capacity of 4, then we can only allow a flow of 4 maximum through this edge. Okay, so we cannot add more items, or we cannot send more items through this edge because this is already full. Okay, so that is the basic idea for a flow network: sending items, or sending a flow from S to T, and you transfer as much as possible, and you are also respecting or following the capacities set by the edges. Okay, so formally, a flow network gets a directed graph G, which we assume to be connected. So it's not disconnected. There is only one connected component. Okay, we'll also be given a source vertex S and the sink vertex T, which is also known as the target vertex. Okay, so a source, which is the start of the flow, and then the sink is where all of the flow ends. Okay, we will assume that the source vertex S produces infinite supply, so it's unlimited in the amount of flow that it can send. It's just that we are limited by the amount of flow that can flow through the network because of the edge capacities. Okay, so the edge capacity will set the maximum amount that can flow through it, and the edge flow is the actual amount that flows through that edge. So for our labels, we usually label them for our edges, sorry, we usually label them with flow over capacity. So if we go back here, we have 2 over 3. This means that there was a flow of 2 over the capacity of 3, okay, for edge SA. And then for here, DE, this is 0 over 1, so there was no flow for this edge with capacity of 1. Okay, so that's usually the edge label, flow over capacity. So the actual amount over the maximum. Now, when we send the flow through the network, we must follow 3 properties. So the first is, I already mentioned this, the capacity constraint. So the flow should not exceed the capacity. So it should range from 0 up to the capacity of that edge. Okay, so flow should be between these values, 0 and capacity. Okay, if the edge A to B does not exist, then of course it doesn't have any capacity because there is no direct edge that connects A to B. Okay, so if we go back here, let's say S to E doesn't have an edge, so the capacity from S to E is 0 because there is no such edge. Okay, so that is the first property, capacity constraint. Next is the flow conservation. For each vertex, the total inflow is equal to the total outflow. So meaning the total flow coming into that vertex should also be the total of the amount coming out. Okay, and this should be true for all vertices except the source and the sink, because of course for the source it's only going outwards, and then for the sink it's only going inwards. Okay, but for the rest of the vertices that are inside the network, the flow network, this should hold true. Okay, so we should conserve the flow. So flow is neither produced nor consumed in the network. Okay, there should be no dagdag bawas, there should be no corruption in between. Okay, so these edges should just make the flow pass through them. So your source is the only one that produces flow, and the sink is the only one that consumes. So intermediate nodes inside the flow network cannot produce, so they cannot add more flow inside, nor can they consume, so they can't also subtract or consume some of the flow. So the producing only happens at the source, and the consumption only happens at the sink. Okay, so that is the second property, which is flow conservation. So before we go to the third one, let me just show you some examples. So except for the sink, the source and the sink, for example here A, the total inflow is 2 because there's only from S to A, right? 2 over 3. And then the outflow is 2 as well because it exited here from A to D with flow of 2. For C, it has an inflow of 5, right? So there's the 4 here and then the 1 here. Okay, so that's 5. And then the exit flow or the outflow is also 5 going out from C to E. Okay, and then lastly, let's check D. For D, there's a plus 2 going in, there's a plus 1 going in, so that's 3 total. And then let's check the going out. So this one is going out, so 1, and then this one is also going out, so plus 2, so it's also 3. So the ingoing flow and the outgoing flow is equal for each vertex that is not the sink or the source. Okay, so that is flow conservation. Next, and the last property for the flow would be skew symmetry. And for skew symmetry, this just means that the flow from A to B is equal to the negative flow from B to A. So if it's going backwards, ang flow in the opposite direction, then we'll take the negative. Okay? So we'll call this the net flow from A to B, ang flow of AB. Okay? Because there could be negative incoming flows in the opposite direction. So we'll just sum it up, the positive or the forward flow and then the backward flow. So we'll sum that up and we'll call it the net flow from A to B. Okay? So those are the three properties for flow networks. Some terminology, a path is called a feasible path if it follows the three properties. So if it follows capacity constraint, flow conservation, and skew symmetry, then it's feasible, meaning it's valid. Okay? Next is a saturated edge. So an edge is saturated if the flow that passes through that edge is equal to the capacity. So it means that it's already a full edge. Okay, it's fully saturated. On the other hand, an avoided edge is something that has a flow of 0. Okay, so there is no flow going through that edge, so we avoided it. Okay. Next is the flow size, which is just the sum of all the flow going either out from the source or going into the sink. Or basically you can think of it as the total quantity or the total flow being sent from S to T. Okay, so that is the flow size, so the total flow of the network. Okay, so now that we are familiar with flow networks and flow size, so we are now ready to define the maximum flow problem. So for the maximum flow problem, our input is a flow network, and then so of course this comes with a directed graph, a source, and a sink vertex. And then for our output, we'll try to find the flow from S to T where the flow size is maximum. So it's the maximum flow problem. So pretty straightforward, right? So the flow size is maximum. Okay, So let's take a look at the Ford-Fulkerson method, which is the method that we will use to find our maximum flow. So as a background, Ford-Fulkerson method was created by Lester Ford and Delbert Fulkerson in 1956. We call this a method and not an algorithm because it's incomplete, okay, or it's underspecified, okay, so it's kind of generic. So it's a method for finding maximum flow, but it's not a specific algorithm because one part of the method, how to find the augmenting path, is not specified. So it just says that find an augmenting path, but it doesn't say how to do it. Okay, so some specific algorithms that implement the Ford-Fulkerson method will do their own way of finding the augmenting path. So as an example, Edmonds-Karp algorithm is a Ford-Fulkerson method implementation which uses the breadth first search, or BFS, for finding the augmenting path. Okay, and then there are other algorithms that implement the Ford-Fulkerson method also that uses a different way to find the augmenting path. Okay, so it varies. Okay, so I'll just discuss what the Ford-Fulkerson method does. Okay, so it's general. It just says find an augmenting path, and then it's up to you how to find the augmenting path. Okay, so at the start, the edge flow, of course, is 0. There's nothing that flows yet. And then we will find an augmenting path at each step. And an augmenting path is an undirected S to T path. Okay, so the crucial part here is that it's undirected. So the augmenting path doesn't necessarily follow the directions set in our directed graph. Okay, so even if the direction is backwards, okay, you can still pass by that edge because anyway, you can have a negative flow or a backwards flow. So remember our skew symmetry earlier where we said that flow of AB is equal to negative of flow BA, right? So because of that, we are allowed to pass by edges even if they are not in the correct direction. So okay, so I'll write it down. So it was the flow of AB is equal to negative flow of BA. Okay, so even if it's like this, you can still send a flow from A going to B, because it's undirected. Okay, so we don't follow the direction in the augmenting path, but then we will have to reverse that flow, so it's a negative value. Okay, so I'll show you how exactly that looks like in a while. But yeah, at each iteration we'll try to find this augmenting path, which is just a path from the source to the sink. Okay, and it's undirected. So once we find this augmenting path, so we will increase the flow on the forward edges if it follows the correct direction, okay, provided that that edge is not yet full. Okay, and if it's a backward edge, we will decrease the flow on that edge. Okay, so what do we mean by this exactly? Okay, so let's say that we have our current graph looks like this. Let's say from A to B, and then to C, and then to T, then this one is from S. And let's say that their capacities are 10, 20, 15, and 7. And let's say that there's already a flow, let's say 5 here, say 5 also. Let's say this one also already has 7, and let's say this one already has, let's say, 3. Okay, so of course there are other parts of the graph that are not shown, but let's say that those are the current flows for each edge. So for this one, what would be their capacities? For this one, the capacity would be 10, right? Because, sorry, it's not 10, but it's supposed to be 5 na lang, because 5 out of 10, so you have a free 5. Here, the capacity is 15. Here, capacity of 8. Here, capacity of 4. Now, what if we send another flow along this one? So, S A B C T. Okay, so how much flow can we send here? So the maximum that we can send is 4, right? Because that would make this full already. So if we send 4 flow, a flow of size 4 here, then this would become 9, right? This would become 9 as well. This would become 7 already. So let's update their current capacity. So this would now be equal to 1 na lang, 1 free capacity. This one would have 11, and then this one would have 0. But how about this one? Since the CB edge, so we're going from B to C, but we are not following the correct direction, right? Because we're supposed to be going this way from B to C, but the edge is from C to B. So we can still allow the edge to pass by this edge, because anyway it's not empty, right? There is a 7, but instead of adding to the flow, we will actually subtract the flow, because remember the skew symmetry property, wherein flow of AB is equal to the negative flow of BA. So if it's in the opposite direction, we actually take the negative. Okay, so instead of adding a flow of 4 here, we'll actually subtract a flow of 4. So this one will become, so minus 4, this will become 3. And we'll actually increase the capacity. So this becomes 12 now. Okay, so instead of adding to that flow, we will actually subtract. So it's like going backwards. Okay, so we can do this because that edge, the flow on that edge was not empty. Okay, and then here we can also add on the forward edges because they were not yet full. But if in the current case, now that CT is already full, right here, 7 over 7 na siya, then we can send more flow to this edge because it's already saturated. Okay, so that's the basic idea for how to use the augmenting path. Okay, so once you find the augmenting path, undirected S to T path, increase the flow on the forward edge and decrease the flow on backward edges. Okay, so we will also keep track of something called the residual graph, which will keep track of the edge capacities, so the current edge capacities that we have. So we will update this when we add the augmenting path that we found to the flow. Okay, so normally if you add a flow to the edge, then you would reduce the capacity, just like what we did. So the capacity of AB will be reduced by the cost of the augmenting path. Okay, so minus the AP cost. However, if it's in the opposite direction, instead of reducing the capacity, we will actually add to the capacity because it's going backwards. Okay, so we'll add the cost of the capacity, the cost of the augmenting path to the capacity. So again, this is because of the skew symmetry property that I mentioned earlier. Okay, so we will keep on doing this. We'll keep on finding the augmenting path, and then we'll add that to the flow until such time that all the S to T paths are blocked by either a full forward edge or an empty backward edge. So if all the forward edges or if all paths are blocked by a full forward edge, so that means that you cannot add more flow going forward because that edge is already full. Or if the edge is blocked by an empty backward edge, so that means that you can also go backwards because it's empty. So you cannot subtract on an empty flow, right? Because it would be negative. So if everything is blocked, then there is no more augmenting path, and then that's the time that we will end our iterations. Okay, so that is the termination condition of Ford-Fulkerson method. So putting all of that together, this is the pseudocode for Ford-Fulkerson method. So given a graph G, we'll start with zero flow, and while there exists an augmenting path, then we'll find that augmenting path. So again, it doesn't specify how do we find that augmenting path. And then we'll try to compute the bottleneck capacity, that is the maximum amount that you can send along that path, okay? Because again, it has to follow the capacity constraint, okay? So what is the smallest amount of, sorry, not the smallest, but the maximum amount that you can send through that path without violating the capacity constraint, okay? And then after finding that out, you'll increase the flow on that path using the bottleneck capacity. So you add the flow if it's a forward edge, and then you subtract the flow if it's going backwards ang edge. So you'll update the edge capacities and then keep on doing this until there are no more augmenting paths that exists. Okay, so that will give you the maximum flow afterwards. Okay, so that's the Ford-Fulkerson method. Now we won't be doing an analysis for this one since it's only a method and it's not an algorithm, so we don't actually know how to find the augmenting path. Okay, so let me just show you a quick example of how this works. So let's say we're given this graph, and let's say that currently we have a magical way of finding augmenting paths, right? So we don't know yet how to find them out, but for now, let's say that there is a method that does this for us. So assuming that our augmenting path finding method gave us SADT, so that is this path, right? S to A, sorry, S to A to D, so that's here, A to D, and then D to T. So what would be the bottleneck capacity along this path? That would be 10, right? Because 10 here, and 15 here. So we can't send 15 because it cannot fit the 10. So it's actually the minimum capacity along that edge currently. So we'll send 10 here. So this would be 10 out of 10, 10 out of 15, 10 out of 10. The next, what if we add a new path, which is SEFT? So if it's SEFT, that would be here on the bottom part. So S to E, E to F, F to T. And since they're all forward edges, then we'll just add the flow along those edges, right? And the bottleneck capacity is also 10, right? So 15, 16, and 10. Minimum is 10. So 10 here, 10 over 16, 10 over 10. Next, what if we found the next path, which is SCDABT? Okay, that seems a little bit complicated, so let's try to see how that looks like. So from S to C, we have that one here. C to D, we have that one here. So it's still forward path. Now from D to A, this is actually following the opposite direction, right? Because D to A is not the edge, but it's A to D. Okay, so we have to take note of that. But from A to B, it's going forward, and then from B to T, it's also going forward. So along this path, how much can we send along this? So it's 5 because of the S to C bottleneck, right? So 5 is here, 5 over 5, 5 over 8, and then here 5 over 9, and then 5 over 10. But on D to A, which is a backward edge, we will actually subtract 5 and not add 5. So we will make this 10 minus 5, so this will become 5 out of 15. Okay? So that is because it is a backward edge. And then finally, our last path is SEFCDABT. So it's quite long. So let's go through it slowly. S to E is here. E to F is here. So it's still there's still free capacity left, right? So 10 out of 15, 10 out of 16, And then F to C is still free. C to D is still free, right? From here to here. D to A is still free. So 5 out of 15, this is not empty. So we can go backwards along this path. And then A to B is still free. B to T, there's still free capacity. So how much can we send along here? So there's only 5 left here. 6, 6, 3, 5, 4, and then 5. So the bottleneck is actually this one with 3 left. So because this is 5 out of 8, so we can only send 3 along this path. So that's why the flow size is 3. So if this is 3, then this becomes 13. So we add because it's forward. 13 also because it's forward. So this becomes 3 out of 6. And then this becomes 8 out of 8. And then for this one, since again it's backward, we won't add but we will actually subtract. So 5 minus 3 becomes 2, right? So 2 out of 15 na siya. And then this one will be added by 3, so this becomes 8 out of 9 and then 8 out of 10. Okay? Now, we'll notice now that so for this one, this is already saturated. This one is also saturated. And in here, this is also saturated. This is also saturated. We can still send 2 here, but we can't pass by this part here anymore, C to D. So this is actually this allows us from moving forward. Okay, so we can't find any more S to T path, so we'll stop here. So the total flow size here is 10 plus 10 plus 8, which is 28. Okay, so we have that one here. So we have a flow of 10 here, 5, 13, 13, 3, 8, and then 2, 8, 8, 10, 10. Okay, so that is how Ford-Fulkerson method works. Okay, so now we said earlier that finding augmenting paths is not specified, right? That's why it's only a method and not an algorithm. So we mentioned earlier that Edmonds-Karp algorithm is an implementation of Ford-Fulkerson wherein it uses BFS to find the shortest path. Okay, now other algorithms could find other paths, augmenting paths. It could be the fattest path or the one with the biggest capacity, or it could be just any random path. So the performance of Ford-Fulkerson actually depends on how you choose the augmenting paths, because different augmenting paths will lead you to different solutions, and some solutions would finish faster or will be solved faster than others. Okay, but for the rest of the discussion, we will try to use the Edmonds-Karp algorithm because we already know how to find the shortest path, which is using BFS. Okay, because remember that if you are just looking for an undirected shortest path, we can use BFS for that, right? Remember, so that's what we'll do. So okay, so let me show you a demo for Edmonds-Karp or Ford-Fulkerson method using BFS as the as the means to find the augmenting path. So for this graph, what we'll do is we will run BFS to find our augmenting paths. Okay, so let's see. Okay, maybe I'll choose yellow. Okay, so let's start from node S, right? Then from S, S can go to either A or B or C, right? Because of these edges, right? S to A, S to B, S to C. And then from A can go to just D, right? And then B can go to either A or D. And then C can go to only E, right? And then next, let's expand it more. From D, you can go to 3 nodes, you can go to C, E, or T, right? Because we have this three, C, E, and T. And now we have found our destination vertex, which is T. So this is the first path that we will try. Okay, so let me encircle this one, SADT. So this is the first path. So for SADT, okay, let me remove these markings first. So that would be here, from S to A to D, and then D to T. So how much flow can you send along this path? So we can actually send 2, right? Because that's the maximum. So 2 out of 2, 2 out of 2, and then 2 out of 3. Okay. So after that, we will continue looking for other augmenting paths. Okay. So we'll continue. From A, you can still go to D, right? Then from D, you can go to 3 places, C, E, and T. And then now you have found SBDT. But for SBDT, if you pass by this one, you actually can't. So SB is possible, B to D is possible, but D to T is not possible anymore because this is already full. So although we found a path here, it's not possible to pass by this path. So SBDT is not possible. So let me write down the first path that we had, which was SADT of size 2, right? So let's continue. From E, you can go to T, and we've found T again. So let's try this one, SCET. Okay, so SCET. So this path here is right here, SCCEET. Now how much flow can we send along this one? We can send 4, right? So 4 out of 4, 4 out of 5, and then 4 out of 5, right? Okay, so we can still continue because this one is not yet full, although SC is already full, so there's no point in expanding this anymore, right? And even SB is still free, right? So let's continue finding augmenting paths. So our second path was SCET with cost of 4. So after that, we'll go to the next level. From C, we can go to E again, and from E, we can go to T again. But again, the problem here is that the AD part of the path is already fully saturated, right? Because AD is already full, 2 out of 2 na siya. So although we reach T, this is not an augmenting path. After that, we'll expand D here. So SBD, from D you can go to either C, E, or T, right? So since we reach T again, let's check. But the problem here again is that DT is already full, right? So this is also not feasible. Now for here, for this one, SBDCET, C will be expanded to E, and then E will be expanded to T. Now we have found another T here, so let's check. SBDET. So it's this one, right? SBDET, this path. So that would be here, SB, BD, DE, and ET. And you are still allowed to send 1 flow here, right? 1 out of 3, 1 out of 1, 1 out of 1, and then you can still add 1 here, so this becomes 5 out of 5, right? So now our um, last edge is, or last path is SBDET with size 1. And I say this is the last because all of the incoming edges to T is already full. So there's no way to send more flow through these edges. So this is 2 out of 2. It's already 5 out of 5. So we can't send more. So this is when we stop. Okay? So that is the demo for Edmonds-Sharp algorithm, or implementation of Ford-Fulkerson using BFS to find augmenting path. Okay? So this was the details. No? So the first path that we saw was SADT, maximum flow of 2. So we add 2 along those paths, and then the remaining capacity would be adjusted. And then the second one was SCET, maximum flow of 4. So we also adjust the remaining capacity. And then the last one is SBDET with flow of 1. So we also adjusted the remaining capacity. And then these are the flows at each edge, right? So the total flow size is 7 because that's 2 plus 4 plus 1. So total flow size of 7. Okay? Now, let's see one more example. This time for this graph, and we'll use Edmonds-Sharp again, or BFS, to find the augmenting path for the maximum flow. Okay, so in the BFS, we'll start with S. Okay, maybe I'll redo this one so that I'll start at the very top. So we start at S, and then S could be expanded to A, C, and E, right? Just either A, could be C, or it could be E. Now from A, you can get to either B, C, or D, right? B, C, or D. Then from C, you can get to D or E, right? And then from E, you can only get to F, right? Now, from B, you can go to either D or T. Now, we have found T, so let's check this path here. So, let's check this path, SABT. So for SABT, where is that? It's here. SAABPT. Okay. Now how much flow can we send along this path? We can send maximum of 9, right? Because this is the bottleneck here, 9, A to B. So if it's 9, then this will have 9 out of 10, 9 out of 9, and 9 out of 10, right? Okay, so let's go to the next one. Try to expand C. So from C, you can still go to D or E, right? And then from D, you can go to F or T. So this is just BFS, right? You're just expanding the nodes based on their neighbors. But since we've found another T here, which is the sync vertex, then let's check let's check this one. So SADT. Okay, so it's in here, SADT. So if it's SADT, where is that? That would be here. SAADDT. So along this path, how much can you send? You can actually only send one, right? Because this one only, SA only has a remaining capacity of 1 because it's already 9 out of 10. So if we send 1 here, then this becomes 10 out of 10. This becomes 1 out of 5, 1 out of 15, and then 1 out of 10, right? So you'll also notice that SA, the branch SA is already full, right? So we could actually ignore the branch SA already because we know that even if we find a path from S to T, we can't pass through SA because this edge is already full. Okay, it's already fully saturated. So we can ignore the other nodes here. We don't need to expand those anymore because we know that SA is already full. So let's focus on the next part, which is the SC and the SE parts. Okay, so let's go back to yellow. So from D, you can get to F or T. And then we found another T here. So let me use another color. Okay, so SC DT. Right, so this is our third path that we found. SCDT. SCDT here. So SCDT. How much can we send along that path? So that is this one, SCCDDT. So we can actually only send amount of 5, right? So 5 here, 5 here, and then since this will be added by 5, this will become 6. So 1 plus 5 is 6, right? So we added 5 along SCDT. And then after that, okay, we'll expand E here. So from E, you can go to F, right? By the way, we'll also notice that from S to C, it's already full. So we don't also need to expand these parts here anymore because we know that even if we find a T here somewhere, right, it won't be passable because of the SC. SC is already full, 5 out of 5. So we'll just focus now on the SE part, SEF. Okay, so let's continue with F. So from F, you can go to 2 places, either C or T, right? So from F, you can go to C or T, and now you've found another T. So let's check if we can pass by that. So okay, maybe 200. I like the first one better. Okay, maybe we'll use orange here. So SEFT is our 4th augmenting path, right? So SEFT. Now how much can we send here? And that is actually really open. So SEFFT. So we can actually send 10 along this path because the bottleneck is this one, F to T. Sorry. Yeah, so that's 10 out of 10. Okay. Now, can we still send more? So there is still an open slot here, 10 out of 15. So we can still send up to 5. And then there's still 9 out of 10 here. So there is still a chance that we could find an augmenting path. So let's continue. So from C, you can go to either D na lang, right? We can't go back to E because it's already part of the path, right? Because if you go back to E, then obviously you're just doing a loop. Okay, so from D, where can you go? You can either go to F or T, but since F is already visited along this path, we can go directly to T. Okay, so that is the next the next na path that we'll use, maybe I will use okay, maybe red, then something like this, maybe. It's not visible, so let's just use red. uh, 10. Okay, so SEFCDT is our last path. Okay, so that's SEFCDT. So how much can we send along that path? So where is that path? It's here. S to E, E to F, F to C, it's still a forward path, C to D, D to T. So it's all forward paths. So how much can we send here? We can actually only send 3 because the C to D is the bottleneck, 5 out of 8. So the remaining capacity is only 3, right? So we'll update this. We'll make this, that was once 10, right? So if we add 3, this will become 13. Then this one will become 13 as well. Along this one, it will be 3 out of 6. Then this one will be 8 out of 8. And then this one will be from 6. So this becomes 9 out of 10. Okay? So now, this is already the final set of augmenting paths, because even if you expand the rest, you can't find any more. Okay? So we have SABT, SADT, SCDT, SEFT, SEFCDT. So what is the total size of the flow? So the total flow size is how much? Total flow is equal to, so this is 10 plus 15, 25 plus 3, that's 28. Okay, and let's check. So this one you have plus 10 plus 5 plus 13. So from S going out, it's 28. And then from T going in, you have 9 plus 9 plus 10. So that's 18 plus 10. So going in is also 28. Okay, so that is our example for this graph using the Ford-Fulkerson method, specifically the Edmonds-Karp algorithm. Okay, so these were the paths that we found, and that was the flow size. Okay, so that is the demo for maximum flow. Now, what are some applications of maximum flow? Why are we interested in this problem? So you can use this for transportation, right? So how do you find the cost-effective way to ship goods from a factory to warehouses to retail stores? Okay, so from the factory, which is the source, to retail stores, which should be your sink. Okay, and then from warehouses, those are your intermediate nodes. And warehouses shouldn't consume nor produce goods, right? So they should just pass it along to other nodes, to other warehouses, or to the other retail stores. Okay, you can also use this for bipartite matching. So let's say that you're given a set of job applicants and applying for jobs. Try to find a matching that maximizes the number of applicants selected for the jobs that they are qualified in. So if you remember this from ComSci 57, you can solve bipartite matching using the Ford-Fulkerson method. Okay, and this was also used somewhat during the Cold War. Okay, so during the Cold War, Soviet Union was connected to Eastern European countries using a railroad network. Okay, and they wanted to send goods, of course, or supplies from the Soviet Union to the Eastern European countries. So they wanted to maximize the flow of supplies along this rail networks. Okay, so that is a maximum application of a maximum flow problem. Okay, so that is maximum flow. Now let's look at another problem, which is called min-cut problem, and this is actually somewhat related to maximum flow. So before we discuss min-cut, let's try to discuss first what is a cut in the first place. So a cut is just a partition of vertices into two disjoint subsets A and B. Okay, so you partition or you divide the vertices into two subsets A and B, such that all vertices are part of the either A or B, so that if you take their union, it would be all vertices, and there are no intersections, so they are disjoint subsets. Okay, the other condition here is that for your graph, if you have a source and a sink vertex S and T, S should belong to one subset and the T should belong to the other subset, so they shouldn't be part of the same subset. Okay, so again, the source should be in subset A, the sink should be in subset B. So that is the condition. And then we will define cut capacity as the sum of edge capacities for edges x to y, such that x is in A and y is in B. So that means that they are the edges that cross the cut or the partition. Okay, so we'll sum up all of the edge capacities of those edges. So how does that look like? So let's say that this is your graph, this is your flow network, and this is the source, this is the sink, S and T, and let's say that we partitioned it like this. So one partition contains SAB, the other partition contains CDT. So the cut capacity is actually here. So remember that cut capacity is the sum of edge capacities of edges x to y, such that x is part of subset A and y is part of subset B. So which edges are those? So we actually have two edges. That would be edge AC here, because the starting point is in subset A, which is this one, and the destination is in subset B, right? And then there's also BD that crosses this partition, so from B to D. So if you sum up the edge capacities of 10 plus 5, you get the cut capacity of 15. Now, how about C to B? Is this not included? Well, it's not included because although it crosses the partition, it doesn't follow the definition, because edge CB starts from B and goes to starts at partition B and goes to partition A. So it's the opposite direction. So we'll only follow this direction. So X should be in partition A and then Y should be in partition B. Okay? So those are the edges that we'll use to compute the cut capacity. Okay. So given this graph, there are actually many ways to cut the graph, right? So we could either partition it like this, like partition is here, and then the rest of the other vertices. And this is valid because S belongs to one partition and then T belongs to the other partition. If this is the case, how much is our cut capacity? So it would be 10 plus 5, that's 15, and plus 5, this would be 30, right? Now another cut here would have been something like this. Maybe if we grouped this 4 together and then this 4 together. Again, this is a valid cut because S and T belongs to different subsets. Now if this is the cut, what would be our cut capacity? So that's 9 here plus 15, so that's 24, plus 8, that's 32, and then plus 16, 48. So it's actually a bigger cut than the previous one, which only has 30, right? We did not include this one, the F to C, because it's going backwards. And then we can also do it like this. Like if we choose all of them in one partition and then isolate T as one cut. If this is the cut, the capacity would be 10 plus 10 plus 10. It's also 30. Okay? You can even do it like this. Like, what if it's something like this? Like, pa-diagonal siya. Like this, and then like this. It's also possible, right? So, there's a lot of ways that you could cut the graph such that S and T belongs to two different subsets. Okay? So, with that being said, let's define the min-cut problem. So, for the min-cut problem, our input is a positive edge-weighted digraph or a directed graph, G. So, let's just assume that all the edges are positive, okay? And we still have the source vertex and the target vertex T. Okay. Our output is an ST cut, so meaning we will cut the graph such that S and T are, they belong to two different subsets where the cut capacity is minimum. So, earlier we saw that different cuts have different cut capacities, but which cut has the minimum cut capacity? So that is what we're trying to find out. Okay? So, because that cut is the cheapest way to disrupt all flow from S to T. Okay? That is the minimum cut. So, if you cut along that line, then all flow from S to T would already be disrupted. Okay? So, an application of this is also in the Cold War. So, earlier, in maximum flow, Soviet Union wanted to send goods to the Eastern European countries. But in min-cut, it's the US, United States of America, wants to find the cheapest way, which is the minimum cut, to cut off supplies, the transport from the Soviet Union to Eastern European countries by destroying railroads. Now, of course, they could destroy all railroads, but that would take too much time and effort. So, what would be the minimum amount or minimum set of railroads to cut such that everything is cut off? Okay, so they will destroy a minimum amount of railroads so that everything from Soviet Union will not reach Eastern European countries. Okay, so you'll totally cut off that line, the flow. Okay, so that is the min-cut problem. And in fact, max flow and min-cut are actually dual problems, so they are actually related. And their relation is pretty straightforward. The size of the max flow is equal to the min-cut capacity. So the maximum amount that you can send, you can flow, is actually the min-cut capacity as well. Okay, so they are the same. So how do you compute the min-cut if you already have the max flow? So given max flow F, you compute the min-cut by doing the following. A, the first subset would be the set of vertices that are reachable from S while respecting the remaining capacity. So you will do like a traversal from S along other going to other nodes if there is still remaining capacity along that edge. Okay, but if it's already full, then you cannot visit the next node. Okay, and then B, the other subset would be the unreachable vertices. Okay, and that is how you will partition the two. So let's say this is our graph. Okay, this already has a flow, right? So let's see how much is the maximum flow here. The max flow, we can compute that just by looking at the flow going out of S or going into T. So from S, you get flow of 10 plus 5 plus 13. So this is actually 28. And that's the same for T, right? You get 8 plus 10 plus 10. That's here, 8, 10, and 10. And then for S, that's 10, 5, and 13. This is also 28. So the max flow size is 28. So we'll expect the min cut also to be 28. Now, how do we find out the min cut? So we will start at S. Okay. So S is here. So S is discoverable. And then we will try to search or try to find out which nodes are reachable. Now, can S go to A? S to A is already full, so we cannot pass by this edge. Okay? Same with S to C, because S to C is already full, so we can pass by here as well. Now, S to E is passable because there is still remaining capacity here of 2, so E is reachable this time. Now, from E, which nodes can we go to? We can go to F because E to F still has remaining capacity, right? So there's still remaining 3. So F is also reachable now. From F, can you go to T? Well, you can't because it's blocked off by the 10 over 10 na flow. F can go to C because there's still remaining flow of 3 here, right? 3 out of 6. So C is also reachable this time. Now from C, can you still go to D? Well, you can't because it's blocked off by 8 over 8. Can you go to A? Well, you also can't because you can't do a backward flow here because it's already empty. So 0 out of 4, right? So you can't do a backwards flow. Same with F to D. You can't do a backwards flow here, so because it's empty, so it's not passable. So we are actually stuck at C. We can't do go further. So this would be our partition. So the reachable nodes that are reachable from S are S, E, F, and C. And those that are not reachable are, so this is one group, S, E, F, C. Okay? And then the not reachable non-reachable nodes are A, B, D, and T. So that is this group. Okay? So now this is already our cut. So the min cut is the two partitions S, E, F, C and A, B, D, T. Okay? So that is the minimum cut. And if we just clear this out and do it again, so if it's S, C, E, T here, S, C, E, F, and then A, D, B, T here, what would be our min cut capacity? So which edges go from A going to B? So let's see. So that would be this edge, right? From S to A. So SA has a capacity of 10, and then AC is not part of it because it's going backwards. We have CD, which goes from C to D, so it also crosses to the other subset. So CD is 8. DF is not part of the edges because it's going backwards. And then finally we have FT, which is going from F to T, subset A to subset B, right? So FT, capacity of 10. So this is also 28. So the min cut capacity was also 28. Remember, our max flow capacity was also 28, right? Because of the 10 plus 5 plus 13 here. So they were the same. Okay? So that's it. Max flow 28. Reachable from S is the 4 nodes. And then this is your min cut. And then the min cut edges would be used to compute the capacity, which is also 28. So this is the final cut for this flow. Okay, so that's it for min cut. Okay, so to review, we talked about maximum flow problem, and we introduced the flow networks wherein you have a source vertex and a sink vertex, and your goal is to transfer as many or as much items or flow as possible from S to T. right? While um, following the capacity constraint, or the capacity of each edge, right? Um, we introduced the Ford-Fulkerson method, which is a general method to find maximum flow. It's only a method and not an algorithm, because it's not specified how you actually find the augmenting path, right? So you find an augmenting path, and then you add the path cost to the flow if it's forward, following the forward edge, and then if it's backward edge, then you subtract it. Okay. And then we also talked about the dual problem of minimum cut, which is the partner of maximum flow, and found out that we can easily compute the minimum cut from the maximum flow, right? So just um, go through the reachable edges from the source vertex following the current capacities, and those that are reachable belongs to one partition, and then the rest that are not reachable belongs to the other one. Okay, so we also found out that maximum flow capacity is equal to the min cut capacity. Okay, so that's it for this lecture. If you have any questions, please don't hesitate to ask, and I will see you next time.